everyone, welcome to the second crash course of topic 1 of unit 1 IAS chemistry. In the previous video I discussed about topic 1A. So in today's video we will be doing topic 1B. So when we start off topic 1B, we have to be able to write chemical equations. So the basic in that is we have to be able to write formulae for names. So for example, I took here iron 3 hydroxide. So the first step we have to do is we have to write the symbols. So iron we know is Fe, hydroxide is OH. So we write those down. Then after that we have to write down the charge. So Fe3 means its oxidation number is 3. So we write 3 plus here. Then here we have OH. So we have to remember that OH has a -1 charge. So we write that down. And then after that we cross the charges. So that means we multiply Fe by 1, we ignore the sign, so we multiply Fe by 1 and OH by 3. So that gives us a neutral compound which is FeOH thrice. So then we have to be able to write an equation from a description. In this example, carbon dioxide gas and calcium hydroxide solution, which are the reactants, they react to form calcium carbonate precipitate, which is a solid, and water, which are the products. So here I wrote down carbon dioxide, and then we write this formula for calcium hydroxide the same way we derive the formula for iron 3 hydroxide. Same thing for calcium carbonate, and water is H2O. The next we have to be able to balance chemical equations. So this is a very basic thing, but we have to get it right. And so how do we balance an equation? So balancing an equation means making both sides of the equation have the same number of each atom, and also making sure that both sides have the same final charge. So in this example, CH4 plus Cl2 gives us CCl4 plus HCl. So I want you to ignore these four for now, and so we'll start off with the carbon atoms. So here we have one carbon atom, and remember this is Cl, not carbon, so this is chlorine, not carbon. So here we have only one carbon atom, so the carbon atoms are balanced. Then we move on to the hydrogens. Here we have 4 hydrogens, but here we have 1 hydrogen. So what we do to balance the hydrogens, we write a 4 over here. We write this 4 over here. But by doing that, now our chlorines are unbalanced. So now here we have two chlorines. Here we have 4 plus 4, 8 chlorines. So to balance the chlorines, we write a 4 over here. So 4 into 2 gives us 8 chlorines on this side, 8 chlorines on this side, so it's balanced. Here I have included 3 small exercises for you all. So what you all can do is you all can pause the video and attempt these 3, and then once you all are done, you all can resume the video and check your answers. Okay, now we'll discuss the answers. So for the first one, we have H2 plus O2 gives us H2O. So all the hydrogens are balanced. See, we have 2 hydrogens here, so they are balanced. But the oxygens, we have 2 oxygens here, but only 1 oxygen here. So we write a 2 over here. We write this 2 over there. But by writing that 2, we unbalanced our hydrogens again. So we have 4 hydrogens here, but only 2 hydrogens here. So we write a 2 here. That gives us 4 hydrogens in total. So it's balanced. Then in the second one, aluminium plus chlorine gives us AlCl3. So we start off with the aluminium. So we have 1 aluminium atom here, 1 here, so it's balanced. Then we move on to Cl. Here we have 2 Cl, but here we have 3 Cl. So how do we balance this? We have to find the lowest common multiple, which is 6. Of 2 and 3, the lowest common multiple is 6. So we have to make sure both sides have 6 chlorine atoms. So how do we make this side have 6 Cl atoms? We write a 3 here. So 3 into 2 gives us 6 Cl atoms in total on this side. How do we make this side have 6 Cl atoms? We write a 2 in front of this. So then we get 2 into 3 gives us 6 Cl atoms. But by writing that 2, we have now unbalanced our aluminium. See? So what we have to do is we have to write 2 over here, then that way our aluminiums are balanced. Then the next one, Fe plus H2SO4 gives us Fe2SO4 3 plus hydrogen H2. So what do we do first? We start off with Fe. So 1 Fe here, 2 Fe's here. So we put a 2 over here to balance the Fe. Then we go to the hydrogens. We have 2 hydrogens here, H2, and 2 hydrogens over here, H2. So hydrogens are balanced. Then we move on to the SO4 group. Here we have 1 SO4 group. Here we have 3 SO4 groups. So what do? We write a 3 over here. So we write 3 over here. Then after that, our SO4 are balanced, but now our hydrogens are unbalanced once again. So here on this side we have 6 hydrogen atoms. On this side we have 2. So we need to make this side have 6. So we write a 3 here. So 3H2. So next we move on to state symbols and arrows in equations. So state symbols are more often than not, they are an essential component of having a complete equation. So S means it's solid state, L means liquid state, G means gaseous state, and AQ within brackets means it's aqueous, so it's dissolved in water. Then moving on to the arrows. So these are the type of arrows we commonly find. So we have the conventional left to right arrow. So that's what we more often than not come across. But then here we have this reversible arrows. So this arrow represents that the reaction can go in both directions. Next we move on to ionic equations. So ionic equations show atoms or molecules involved in a reaction, but they only show the ions that react, and they omit the spectate ions which do not react. So the spectate ions are there in the same state on both before and after reaction. So the below steps can be followed to simplify and obtain an ionic equation. So what do we first do? We start with the full normal equation. Then after that we replace the formulae of all the ionic compounds by their separate ions. So if it's sodium chloride, we write it as Na plus and Cl minus. So then we have to delete any ions that appear identical on both sides. So these identical ions are what we call the spectate ions. So nothing happens to them. Then important point to remember is that ionic compounds can only be dissociated or like separated into the ions if it is in aqueous medium. So if it's in solid, it cannot dissociate into separate ions. So if it is in aqueous medium, we can separate them and write, or else we have to write it as the compound itself. Here we have an example of an ionic equation. So this is the full equation, the balanced full equation. H2SO4 plus 2KOH gives K2SO4 plus 2H2O. So then how do we write the ionic equation? So H2SO4, it's in aqueous medium, so we can dissociate the ions. So it's made of two H plus ions, so we write the H plus ions separately. SO4 minus SO4, oh, this should be minus, sorry. This is not 2 plus, this is 2 minus. And so we separate these two. Then after that we have 2 KOH. So then we separate these two also into K plus and OH minus ions. 2K plus, 2OH minus. Then here on the product side we have K2SO4. It's in aqueous. So then we separate it into 2 K plus ions and 1 SO4. Again, this is not 2 plus, this is 2 minus. And water is a covalent compound, so we cannot separate it into its ions, so we write it as water. Then now we have to identify the spectate ions and cross them out. So here we can see that the sulfate ions, the SO4 2 minus ions, they appear identical. See, they are identical. Then the 2K plus ions, they are also identical. So we cross them out. So then our final ionic equation is 2H plus aqueous plus 2OH minus aqueous gives us 2H2O liquid state. Next, ionic half equation. So these are usually used to show oxidation and reduction, and they show us what happens to only one reactant. So for example, the reduction of copper ions, here we can see Cu2 plus uh, gains 2 electrons to form a copper atom. So reduction is the gain of electrons. So then we move on to the types of reactions. So we have metals reacting with acids. So this is the general equation. So any metal that reacts with acid will give us a salt and hydrogen. So when hydrogen is formed, we can observe effervescence of the gas or bubbling. And then if the salt is a soluble salt, then a solution forms, and the metal must be also reactive enough. So here we have an example, magnesium reacting with hydrochloric acid to give us magnesium chloride and hydrogen gas. Then we have metal oxides and insoluble metal hydroxides reacting with acids. So metal oxide plus acid gives us salt and water. So this is the general equation. Metal oxide plus acid gives us salt and water. Metal hydroxide plus acid also gives us salt and water. So more often than not, a solution will form, the salt will dissolve. The metal's reactivity does not matter as it is present in ions and not in atoms. So metal oxide is an ionic compound, metal hydroxide is also ionic compound, so it exists, and the metal exists in its ion. So then here we have an example, copper oxide plus sulfuric acid gives us copper sulfate plus water. And another example, zinc hydroxide gives us plus sulfuric acid gives us zinc sulfate, the salt, plus water. Then we move on to acids reacting with alkali. So acid react with alkali to always give us a salt and water. So metal hydroxides that dissolve in water are called alkalis. So when we react an acid and an alkali, we cannot see anything much without an indicator, but a temperature rise can be detected. And ionic equation for all neutralization reactions are H plus OH minus gives us H2O. So this is a neutralization reaction, as the H plus ions, these are found in acids, and OH minus ions found in alkalis as they react to form water. So for example, we have HCl, hydrochloric acid, plus NaOH, which is a alkali, gives us a salt, sodium chloride plus water. Next we have metal carbonates reacting with acids. So this is the general equation. Metal carbonate plus acid gives us a salt, water, and carbon dioxide gas. So when this reaction occurs, carbon dioxide gas bubbling can be seen, effervescence. So this gas, we can use this gas to pass it through lime water, and if the lime water turns milky, we can confirm that it is carbon dioxide gas. And if the salt is soluble, then again a solution is formed. And this reaction is also considered a neutralization reaction, as the H plus ions in the acid react with the carbonate ions in the metal carbonate. So for example, lithium carbonate plus hydrochloric acid gives us the salt lithium chloride plus water plus carbon dioxide gas. Next we have metal hydrogen carbonates reacting with acids. Metal hydrogen carbonate plus acid will always give us a salt plus water plus carbon dioxide gas. So it's similar to, it's pretty much the same as the products obtained with metal carbonates. So this is the general equation. So hydrogen carbonates are compounds that contain this ion. This ion, HCO3 minus ion, is called the hydrogen carbonate ion. So when this reaction occurs, carbon dioxide gas bubbling can be seen. Then again we can use the lime water test to see if it is carbon dioxide. And so this is the example. Sodium hydrogen carbonate plus hydrochloric acid gives us the salt sodium chloride plus water plus carbon dioxide gas. Next we move on to displacement reactions. So So in these reactions, one element will displace or replace another less reactive element in a compound. So metal displacement reactions in aqueous solution. So in this example, we'll take magnesium is added to copper 2 sulfate solution. So we know magnesium is more reactive than copper. So here I have included the reactivity series. So we need to be able to have an idea of the reactivity series. So here magnesium is more reactive than copper. As you can see, magnesium is higher in the reactivity series. So it displaces copper. So it displaces copper from copper sulfate, so it gives us magnesium sulfate and copper as a solid. So the copper ions are reduced to copper atoms. So the blue solution, which is given by the Cu2 plus ions, turns colorless if magnesium is in excess. Then we have halogen displacement reactions. So halogens are the group 7 elements. So reactive halogens displace less reactive halogens. So as you go down the group, the reactivity of the halogen decreases. So fluorine, which is the most reactive, is on top. So here we have chlorine reacting with potassium bromide to give us bromine and potassium chloride. So chlorine is the more reactive halogen, so it displaces bromine, which is the less reactive halogen, to give us KCl. Next we move on to precipitation reactions. So these are reactions in which an insoluble solid, or more often known as a precipitate, is formed when two solutions are mixed. So an example of the precipitation reactions can be the carbon dioxide test. So when carbon dioxide gas is bubbled through aqueous calcium hydroxide, or known as lime water, a white precipitate of calcium carbonate was formed, turning it milky. So this is the identification test for carbon dioxide. So this is the equation. Then sulfate ion test. So when barium ions are added to sulfate containing compounds, barium sulfate, which is a white color precipitate, is formed. So this is the test for sulfate ions. So we add barium ions. That will give us this compound, this barium sulfate. It's insoluble, so it forms as a precipitate. It's white colored. Then we have the halide ion test, so the group 7 ion test. So to do the group 7 ion test, we add silver ions, Ag plus ions, silver ions to halide containing compounds. So these, when this reacts, it forms a silver halide precipitate. So it's either AgCl or AgBr. It will always be an insoluble precipitate. So the colors, so for chlorine, they give, for chlorine, bromine and iodine, they give different colors. We will learn those later. Then precipitation reactions to determine equations. So we will use the example of lead nitrate reacting with potassium iodide to form potassium nitrate, and yellow precipitate of lead iodide. So the precipitate we are forming is lead iodide. So both the reactants, lead nitrate and potassium iodide, they are both colorless. So what we are basically going to do is we are going to place identical volumes of reactants of potassium iodide solution in a series of test tubes. Then we add different volumes of lead nitrate to the tube. So then we place, after we let the reaction occur, then we take each tube and we place it in a centrifuge. So a centrifuge will spin the tubes, and we spin them for the same length of time. Then after that, we measure the depth of this yellow colored precipitate. So there, as you can see in this table, these are the results we obtain. There is no increase in the depth of the precipitate after tube 5. So as you see here, we increase the volume of lead nitrate added. So as we increase that volume, the depth of the precipitate also increases up to tube 5. Then after tube 5, the more, even though we add more lead nitrate, the depth of the precipitate remains the same. So that means the reaction has been completed after tube 5. So all we are doing is we are adding excess lead nitrate solution. So the reaction was incomplete in tubes 1 to 4, but after tube 5 it was complete. So we'll use tube 5 reactant quantities in our calculations. So the number of moles of potassium iodide 0.005 into 1 gives us 0.005 moles, and the concent, so this 1 is the concentration of the solution in moles per decimeter cube, and we had to convert this 0.005 is the volume of potassium iodide. It's in centimeter cube. Here we have to convert it to decimeter cube, so we divide it by 1000, which gives us this value here. Do the same for lead nitrate. So this is the amount of moles we get for each reactant. So if we use the ratio, we can determine that lead nitrate and potassium iodide react in the ratio of 1:2. So we divide 0.005 by this. So then we'll get the ratio is 1:2. Therefore, we can write lead nitrate plus potassium iodide gives lead iodide plus potassium nitrate. So we know they react in the ratio 1:2. So 1 we don't need to write in front of lead nitrate, potassium in front of lead nitrate. So then we have to write the 2 in front of potassium iodide. So like that we can determine equations using precipitation reactions. That's it for topic 1b. We'll catch you next time when we do topic 1c.